Welcome to Disk Explainer. If you're a junior embedded systems engineer, you are stepping into a seriously fascinating role right now. Think about it like this. Your embedded processor? It's basically an isolated detective locked inside a pitch-black room. It can't just look around to see what's there. Instead, it has to use electrical pings to map out and verify its physical surroundings. And today, we're going to learn exactly how to construct those pings so we can be absolutely sure our hardware is functioning exactly the way we designed it. So let's dive right in.
Here's our roadmap for today's hardware detective work. We'll start with the purpose of memory testing, then move on to testing the data bus, testing the address bus, and doing the actual memory device test. After that, we'll put it all together and finally look at working with flash memory.
All right, part 1. The purpose of memory testing, finding physical faults. Before we test anything, we've got to know exactly what we're dealing with. If we look at the landscape of device characteristics, we've got a few different characters. There's SRAM, which is volatile and byte-writable. Honestly, that makes it pretty straightforward to test. Masked ROM, on the other hand, not writable at all. And then we have flash and NVRAM. Now, keep a close eye on that erase size column for flash. We are definitely going to be coming back to the whole headache of sector-based erasing a bit later in the explainer.
You see, writing memory test code isn't just some abstract software exercise. It is literally the act of checking the physical reality of your board. We're hunting for highly specific physical defects here. We're talking about shorted wires where two data lines are accidentally touching, or open, broken wires. Our code also has to catch improperly seated chips, where a tiny bent pin completely misses its socket. Yeah, the classic cause of a ruined weekend right there. This is the physical, real-world reality our code has to uncover.
Moving to section 2, testing the data bus, the vocal cords.
Okay, before the processor can have any sort of meaningful conversation with the memory, it needs vocal cords. To test those, we use something called the walking ones test. Take a look at this binary sequence. We start with a single 1 all the way in the rightmost position. Then, we literally walk or shift that single 1 bit leftward one position at a time. Now, why do we do this? Well, by walking that 1 across the bits, we successfully isolate each individual data line. Think about it. If two lines are physically shorted together, they'll both show a 1 when only one of them actually should. So this trick lets us isolate every single wire to check for short circuits totally independently. It's just a beautifully simple, highly effective diagnostic.
Next up, section 3, testing the address bus, the map. So, now that the system can speak, we need to check its map to make absolutely sure no memory locations are physically overlapping. To do this efficiently, we rely heavily on power of 2 offsets, and the reason is pretty cool. Think about powers of 2 in binary. 1 is 0001, 2 is 0010, 4 is 010, 8 is 1000, right? In a binary system, a power of 2 address guarantees that exactly one literal address wire is set to high. By testing exclusively at these specific offsets, we can pinpoint faults and test one literal address pin at a time.
Now, the crucial part is exactly how we test these offsets. We use an alternating pattern, like the hex value AAAAA, which in binary is 10101010, just alternating ones and zeros. We write that initial pattern to our power of 2 addresses. Then we take an anti-pattern, like 555555, which is its exact mathematical inverse, 01010101. If we write this anti-pattern to a test offset, we can then go back and easily see if any of the other power of 2 addresses accidentally received that data. If they did, it means our address bus wires are overlapping and we are literally writing to the wrong place.
All right, on to section 4, the memory device test, the brain.
With the vocal cords and the map completely verified, we can finally test the brain itself, making sure the actual memory device can retain complex data over thousands of addresses. What we use here is an increment test, and it relies on a really clever 2-pass logic. In pass 1, we fill up the memory with a known incrementing binary pattern, so every single location gets a unique value. Then, in pass 2, we go back through, verify that original pattern is still there, and immediately overwrite it with its exact inverted value. Finally, we verify that inverted value and zero it out. This exhaustive, bit-by-bit process guarantees that every single bit inside that chip can successfully hold both a 1 and a 0, independently without leaking any data to its neighbors.
Section 5. Putting it all together, the code reality.
Let's bring all these theoretical electrical checks back down to earth and apply them to a 64 kilobyte bank of SRAM.
Just look at how satisfying this piece of C code is. That main if statement perfectly reflects the strict dependency chain we mapped out at the very beginning. First, it runs the data bus test. If and only if that passes, it moves on to test the address bus. And if that passes, it finally tests the device itself. You literally cannot skip steps here. The logic in the software perfectly mirrors the physical reality of the hardware.
And what actually happens when this code runs? We get a physical result. In embedded systems, we usually want to visually alert the engineer to the hardware's precise status instantly. So if any of those functions return a non-zero error, boom, we immediately toggle a red LED. But if all three pass successfully, we get that sweet, sweet green LED. I gotta tell you, it is an incredibly rewarding feeling to see that green light pop on and know your silicon is absolutely flawless.
Which brings us to Section 6, working with flash memory, the curveball.
So everything we've talked about so far works beautifully for SRAM. But what if we throw a curveball into the mix? What if we are testing or writing to flash memory? Well, reading from flash is super easy. It's basically identical to SRAM. The processor asks for an address, and the flash just hands over the data. Easy. But writing to flash, that introduces some major physical constraints that really throw a wrench into this whole testing process.
Let's break down these constraints, because they are critical. First off, flash memory must be erased before it can be rewritten. If you try to skip that, the old and new values just kind of smush together logically into total garbage data. Second, and this is the real kicker here, you cannot erase a single byte of flash. No way. You have to erase an entire sector, or block, all at once. We're talking thousands of bytes wiped out entirely just to change a single bit. So yeah, you can see why our simple bit-by-bit SRAM test just won't work out of the box here.
So, how exactly do we handle this nightmare in our embedded software? Flash drivers to the rescue. We use standard application programming interfaces, or APIs, provided by these drivers. You'll typically see functions like flash erase and flash write. The entire job of this driver is to completely hide all those frustrating sector erasure details from the rest of the system software. Whenever the application needs to save data, it just calls the driver, and the driver manages all the messy physical constraints of the flash chip behind the scenes.
As we wrap things up today, I really want to bring this whole explainer full circle. The purpose of a memory test is to confirm that each storage location in a memory device is working. Always keep that in mind. The C code you write, it's simply a tool. You are essentially using software to validate the physical electrical world.
So I'm going to leave you with this one thought. The next time you sit down to write a memory test, ask yourself, are you just writing loops, or are you interrogating the hardware? If you approach it like the hardware detective you actually are, I promise you, you'll build vastly more reliable embedded systems. Thanks so much for joining me on this explainer, and hey, happy debugging!